Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles with internal length between them. At this point, let's call this point N. Point N is the point of contact between those two circles. They are touching each other at point N, and we also know that AB is the diameter of the big circle. That is to say, AB equals 2 times the radius of the big circle. So let's define the radius of the big circle as capital R. Capital R is the radius of the big circle, and we will define small r as the radius of the small circle. Okay, small r will be the radius of the small circle, okay. Capital R is defined as the radius of the big circle, and small r is defined as the radius of the small circle, and AB is the diameter of the big circle. So AB equals to 2 times the radius of the big circle. That is to say, AB equals 2 times capital R. Okay, and we will define Q. Point Q will be the center of the small circle, and point P will be defined as the center of the big circle. Again, point Q is the center of the small circle, and point P is the center of the big circle. So I write it down. Point Q is the center of the small circle, and point P is defined as the center of the big circle. Point P is the center of the big circle. Okay, so I read again the things that I wrote. Point P is defined as the center of the small circle. Point Q is defined as the center of the small circle, and point P is defined as the center of the big circle. Okay, point Q is defined as the center of the small circle. and point P is defined as the center of the big circle. Okay, this is the center of the small circle, and this point P is the center of the big circle. Okay, and we also know that AC, line segment AC equals to 9 units, line segment BD equals to 4 units. This is a right angle, so actually this angle is also a right angle, because the sum of the angles in any straight line is equals to 180 degrees. For if this angle is 90 degrees, the other angle also must be equal to 90 degrees. And for the same reason, this angle also equals to 90 degrees, because of the fact that the sum of the angles in any straight line in the upper side equals to 180 degrees. So if this angle is 90 degrees, this angle is also equals to 90 degrees. And actually the small circle has 3 tangents. This is a tangent. This tangent is tangent to the circle at this point. Let's call the point of contact between the tangent and the circle point S. So this tangent is tangent to the circle at point S, or it's also called the launch point between the tangent and the circle. Okay, so I'll write it down. Point S point S is defined as the launch point between the circle and its tangent. Okay, point S is the launch point between the circle and its tangent. Okay, and we have second launch point between the tangent to the circle and the circle at this point. Let's call this point point Z. Again, this tangent is tangent to the circle at point Z, or the launch point between the circle and the tangent to the circle is at point Z. And we have also the third launch point between the circle and the tangent to the circle. This is CD, actually is tangent to the circle at this point, point M, or point M is the launch point between the tangent to the circle and the circle. Okay, so points, I'll write it down, that points Z and M are defined as the launch points between the circle and its tangents. Okay, actually points S, Z, and M, again points S, Z, and M are defined as launch points between the circle and its tangents. Okay, in the next step we will draw 3 radiuses from the center of the circle to the launch points. Okay, we'll draw 3 radiuses from the center of the circle, that is to say from point Q to the launch points. So this will be our first radius, small r. So the radius is drawn from the center to the circle, that is to say from point Q until it touches the circle at point S, that is also the launch point between the circle and its tangent. Okay, and I will draw the second radius from the center of the circle, that is to say from point Q to point Z. The radius exits from point Q, that is the center of the circle, and touches point Z, that is also defined as the launch point. And then I will draw the third radius of the small circle from the center of the circle, that is to say from point Q to point M, that is the launch point between the tangent to the circle itself. Okay, so I drew 3 radiuses of the small circle that exits from the center of the circle and touches the 3 launch points of the circle with its tangents. Okay, and we have a rule, I will call it rule number 1. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. Okay, so I will read rule number 1 again. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. Okay, so actually here we have radius that exists from the center of the circle, that is to say from point Q, and touches the circle at point S. So this radius is drawn from the center of the circle to the launch point, that is to say to point S, that is the launch point. So according to rule number 1, the tangent, this tangent to the circle is perpendicular to the radius at the launch point. So okay, because of the fact that the radius is drawn to the launch point, or it touches the launch point, point S, that is the launch point, for that reason the tangent is perpendicular to that radius. So this angle equals to 90 degrees. So whenever you draw a radius that touches the launch point, that is drawn to the launch point, that touches the launch point, then the tangent will be perpendicular to that radius. So this angle is a right angle because the tangent is perpendicular to a radius that is drawn to the launch point, and this radius is drawn to the launch point, point S. Actually it touches point S. For that reason the tangent is perpendicular to the radius, that is to say this angle equals to 90 degrees. And the same thing we have at point Z. Point Z is the launch point between the circle and its tangent. So for that reason the radius will be perpendicular to its tangent, or the tangent will be perpendicular to the radius that is drawn to the launch point. This radius is drawn to the launch point, actually it touches the launch point, point Z, and therefore the tangent is perpendicular to that radius, that is to say this angle is a right angle. Okay, and also we have the same thing at point M. Point M is the launch point between the tangent and its circle. Actually the radius that I drawn to the launch point, actually it touches the launch point, point M. For that reason the tangent is perpendicular to that radius, that is to say this angle is a right angle and this angle is also a right angle. So whenever you draw a radius that is drawn to the launch point, that is to say to point M, then the tangent will be perpendicular to that radius. Actually this radius touches the launch point, point M, and for that reason the tangent is perpendicular to that radius, that is to say this angle is 90 degrees and also this angle equals to 90 degrees. Okay, so actually we have quadrilateral QZMD. Again, quadrilateral QZMD. This quadrilateral has 3 right angles. Okay, 1, 2, and 3. Okay, again, quadrilateral QZMD has 3 right angles. Quadrilateral QZMD has 3 right angles. So the sum of those 3 right angles equals to 90 times 3, that is 270 degrees. Okay, the sum of those 3 right angles is equal to 270 degrees, and we have rule number 2. According to rule number 2, yes, that and according to rule number 2, the sum of the angles in a quadrilateral is equal to 360 degrees. Okay, again I will read rule number 2 again. Rule number 2 states that the sum of the angles in a quadrilateral is equal to 360 degrees, and especially in quadrilateral QZMD, the sum of its angles is equal to 360 degrees. So, in order that the sum of the angles in quadrilateral QZMD will be 360 degrees, the fourth angle must be equal to 360 degrees minus 270 degrees, that is to say to 90 degrees. Okay, so the fourth angle must be equal to 90 degrees in order that in quadrilateral QZMD the sum of the angles will be equal to 360 degrees, because 270 degrees, that is the sum of the angles of the 3 right angles, plus 90 degrees, the value of the fourth angle, will be equal in total to 360 degrees. So the fourth angle of quadrilateral QZMD must be equal to 360 degrees. Okay, so actually this angle must be a right angle in order that the sum of the angles of quadrilateral QZMD will be equal to 360 degrees. Okay, so this angle equals to 90 degrees. Okay, because in total the sum of the four angles will be equal to 90 degrees times 4 is 360 degrees. Okay, so actually we have quadrilateral QZMD with 4 right angles, and According to rule number 3, rule number 3 states that if the sum of the angles of a quadrilateral equals to I made a mistake. Rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle. Okay, so rule number 3 states that, I'll read again rule number 3. Rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle. Okay, so actually quadrilateral QZMD, this quadrilateral has 4 right angles. Therefore, according to rule number 3, quadrilateral QZMD is a rectangle. Okay, so quadrilateral QZMD is a rectangle according to rule number 3. Okay, because of the fact that quadrilateral QZMD has 4 right angles, according to rule number 3, quadrilateral QZMD is a rectangle. Okay? Quadrilateral QZMD is a rectangle. Okay, because it has 4 right angles, and we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. Okay, I will read rule number 5 again. Rule number 5 states that, rule number 4, sorry, I will read rule number 4 again. Rule number 4 states that the opposite sides of a rectangle are equal to each other. Okay, so we know that quadrilateral QZMD is a rectangle. So according to rule number 4, the opposite sides of this rectangle are equal to each other. That is to say, QZ equals to MD. Okay, so according to rule number 4, QZ equals to MD. According to rule number 4. Okay, according to rule number 4, QZ equals to MD. Side QZ of the rectangle equals to side MD, that is the opposite side. Okay, QZ equals to MD according to rule number 4, but we know that QZ is the radius of the small circle. QZ equals to small r because it is the radius of the small circle. So from this equality we can derive that MD equals to small r. Okay, MD equals to small r according to this equality. Okay, MD equals to small r. So here MD equals to small r, and actually we have the other quadrilateral. We have the other quadrilateral SQCM. SQCM is a quadrilateral with 3 right angles, 1, 2, and 3. Quadrilateral SQCM has 3 right angles. Therefore, according to rule number 3, that the sum of the angles in any quadrilateral equals to 360 degrees, this angle must be equal also to 90 degrees in order to complete the sum of the angles in quadrilateral SQCM to 360 degrees. So this angle must be also equal to 90 degrees. So quadrilateral SQCM, this quadrilateral has 4 right angles, and therefore according to rule number 3, this quadrilateral is a rectangle. Okay, and according to rule number 4, the opposite sides of a rectangle are equal to each other. That is to say, SQ equals to CM. SQ equals to CM, and SQ equals to R. So for that reason, CM also will be equal to R. So CM equals to small r, according to rule number 4, that the opposite sides of a rectangle are equal to each other. So if SQ equals to R, CM that equals to SQ will be also equal to small r. Okay, and we will define PM as X, PM equals to X according to our definition. Okay, PM equals to X according to our definition. What is the value of CP? Cp will be equal to Cm minus Pm. Again, Cp will be equal to Cm minus Pm. Very simple. Cp will be equal to Cm minus Pm. Okay? Cp will be equal to Cm minus Pm. Okay? So Cp will be equal to Cm equals to small r, Cm equals to small r, and Pm equals to x. Again, Cm equals to r and Pm equals to x according to our definition. So Cp will be equal to Cm minus Pm, that is to say to small r minus x. Okay? Cp equals to small r minus x. Okay, again, Cp equals to r minus x. Okay, so in the next step we will calculate the radius of the big circle in two different ways. We know that the radius of the big circle equals to capital R, and P is the center of the big circle, so capital R equals to AP from one side. Okay, question number one states that capital R, the radius of the big circle, equals to AP. But we also know that the radius of the big circle also equals to PB. Okay, PB is the radius of the big circle also. So we'll create also question number 2 that states that the radius of the big circle also equals to PB. Okay, so we will calculate the radius of the big circle in two different ways, and then we will compare equation number 1 to equation number 2. Of course, they are equal to each other because those expressions are the expressions of the same radius of the big circle. Okay, so what is the value of the radius of the big circle according to equation number 1? It equals to AP. Okay, the radius of the big circle equals to AP. But what is the value of AP? AP equals to AC plus CP. Again, AP equals to AC plus CP. Okay? AC plus CP equals to AP. Again, AP, the radius of the big circle, equals to AC plus CP. But AC equals to 9 units. It is given us in the question. AC equals to 9 units. And we have already found out that CP equals to R minus X. Here we found out that CP equals to R minus X. Okay, CP equals to R minus X, so AC is 9 and CP is R minus X. We have already found out that CP equals to R minus X. Okay, so in total AP equals to AC plus CP, that is AC is 9 units and CP is R minus X. So the radius of the big circle equals to 9 plus R minus X. So I write it down that the radius of the big circle, capital R, equals to 9 plus small r minus x. But we also know that according to equation number 2, that the radius of the big circle, capital R, equals to BP. P is the center of the circle, of the big circle, so BP is actually the radius of the big circle. Actually, AB, that is the diameter of the big circle, equals to R plus R, or capital R plus capital R. So AB equals to 2R, that is to say to AP, that is capital R, plus PB, that is also capital R. Okay, so PB equals to capital R. But what is the value of PB? The value of PB is actually PM plus MD plus DB. Okay, PB equals to PM plus MD plus DB. Okay, so according to equation number 2, the radius of the big circle equals to PB, that equals to PM plus MD plus DB. Okay, so actually the radius of the big circle equals to PM. The value of PM is x according to our definition. PM equals to x. MD equals to small r. MD equals to small r. So it is x plus small r plus dB. dB equals to 4 units. It is given us in the question. So in total we got that the radius of the big circle according to equation number 2 equals to x plus r plus 4. That is according to equation number 2, but according to equation number 1, the radius of the big circle equals to 9 plus small r minus x. So we can compare equation number 1 to equation number 2, because both those two expressions are expressions for the same radius of the big circle. So expression number 1 equals to expression number 2. Okay, and we will get the equation number 3 that states that the radius of the big circle according to expression number 1 equals to the radius of the same big circle according to expression number 2. Okay, so we will get that the radius of the big circle according to equation number 1 is 9 plus small r minus x, and it equals to the radius of the big circle according to equation number 1 or expression number 2 or expression number 2. Okay, it equals to the radius of the big circle according to equation number 2. That is to say, it equals to x plus r plus 4. Again, equation number 3 states that the radius of the big circle according to expression number 1 equals to the radius of the big circle according to expression number 2, or capital R equals to capital R. Okay, so here we have R in this side of the equation and we have R in the other side of the equation, so we can cancel R. So what left after we cancelled R actually is 9 minus x equals to x plus 4. Okay, that is what is left after we cancelled R. 9 minus x equals to x plus 4. Here we will add 4 to this equation number 3, and we will subtract 4 from equation number 3, and we will get that 9 minus 4 is 5 minus x equals to x. Okay, 5 minus x equals to x. So here we will add x to this equation, and we will get that 5 equals to 2x. We got the equality that states that 5 equals to 2x. Here we will divide equation number 3 by 2 in order to get the value of x. We will get that x equals to 5 over 2. 5 over 2 is 2.5 units. So we got the value of x. X equals to 2.5 units. Okay, x equals to 2.5 units. But we have equation number 1 for the radius of the big circle that states, according to equation number 1, the radius of the big circle equals to 9 plus small r minus x. That is equation number 1. Equation number 1 states that the radius of the big circle equals to 9 plus small r minus x. But we know that x equals to 2.5 units, so we can substitute x in equation number 1 by 2.5 units, and we will get that the radius of the big circle, according to equation number 1, will be equal to 9 plus r minus 2.5. We substituted x by 2.5. So here we will get that the radius of the big circle equals to 9 minus 2.5. 9 minus 2.5 is 6.5 plus small r. Okay? So we got that the radius of the big circle equals to 6.5 plus small r, plus the radius of the small circle. And we already know that x equals to 2.5 units. Okay, so in the next step, I will present a new rule, rule number 5, and we will implement rule number 5 in our drawing, in our two circles. Okay, so rule number 5 states that if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so I will read rule number 5 again. Rule number 5 states that if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So actually, if we have two circles that are touching each other internally, then according to rule number 5, the distance between their centers equals to the difference between their radiuses. So if the distance between their centers is d and their radiuses are r1 and r2, then d will be equal to r1 minus r2. Okay, again, if the distance between the centers of the two circles that have internal lunge between them is d, then d will be equal to r1 minus r2. The distance between their centers is equal to the difference between their radiuses. That is to say, d will be equal to r1 minus r2. Okay, so we can implement rule number 5 in our two circles, because those two circles have internal lunge between them at point N. Again, those two circles have internal lunge between them at point N. They are touching each other at point N internally. Therefore, according to rule number 5, the distance between their centers, that is to say QP, because Q is the center of the small circle and P is the center of the big circle. Therefore, the distance between their centers is QP. QP will be equal, according to rule number 5, to capital R minus small r. Okay, so the implementation of rule number 5 in our two circles is that QP, the distance between the centers of those two circles, is equal to capital R minus small r. Okay? Again, the distance between the centers of those two circles is QP, and it equals to capital R minus small r. That is the difference between the lengths of the radiuses of those two circles. Okay, QP equals to capital R minus small r. So here we will add small r to this equality, to equation number 4, and we will get that capital R equals to QP plus small r. We got the radius of the big circle. The radius of the big circle equals to QP plus small r. Okay, but we have already know, according to equation number 1, that the radius of the big circle equals to 6.5 plus small r. Okay, the radius, according to equation number 1, the radius of the big circle equals to 6.5 plus r. So here we have two expressions of the radius of the big circle. Okay, of course they are equal to each other because we are talking about the radius of the big circle. So we can compare equation number 1 to equation number 4 and create equation number 5 that states that capital R equals to capital R. Okay, both of those two expressions are expressions for the radius of the big circle, so they are equal to each other. Okay, so we create equation number 5 that states that the radius of the big circle, according to equation number 1, equals to the radius of the big circle according to equation number 4. Okay, we got equation number 5 that states that 6.5 plus r equals to QP plus r. Here we have r in this side of the equation and we have r on the other side of the equation, so we can cancel r. After we cancelled r, we get that QP equals to 6.5 units. Okay, so QP equals to 6.5 units, so the distance between the centers of the two circles is 6.5 units, and we have already know that x equals to 2.5 units. Okay, so here we will connect together points Q and P by a straight line. So we have here triangle Q and P, triangle Q and P in the green color is a right triangle because of the fact that angle Q and P is a right angle, therefore triangle Q and P is a right triangle. Okay, so I write it down. Triangle Q and P is a right triangle because angle Q and P is a right angle. So therefore we can implement the Pythagorean theorem in the right triangle Q and P. We can implement the Pythagorean theorem in this right green triangle. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP squared, that is the square of the hypotenuse, equals to sum of the squares of the perpendiculars, equals to PM squared plus QM squared. That is the square, the sum of the squares of the perpendiculars. So we got this equality according to the Pythagorean theorem. Again, we got this equality according to the Pythagorean theorem in the right triangle QMP. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. But we know that QP equals to 6.5 units. We have already found out that QP equals to 6.5 units and X equals to 2.5 units. Okay, QP equals to 6.5 units, therefore QP squared is 6.5 squared equals to PM squared. PM equals to X according to our definition, and as I've already showed you, X equals to 2.5 units. So PM squared is X squared, that is actually 2.5 squared, plus QM squared. QM is the radius of the small circle, so QM squared is R squared. Okay, so we got that 6.5 squared equals to 2.5 squared plus R squared. 6.5 squared is 42.25 and 2.5 squared is 6.25. So I write it down. So we got that 42.25 equals to 6.25 plus R squared. Here we'll subtract 6.25 from this equality, and we will get that 42.25 minus 6.25 is 36 equals to R squared. Here we will take a root out of this equality, and we will get that r equals to the root of 36. The root of 36 is 6, so we got that the radius of the small circle, that is to say small r, equals to 6 units. So the answer to the question is that the radius of the small circle, this small circle, equals to 6 units. Okay, now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. We have here two circles that have internal length between them at point N. They touch each other internally at point N. Point N is the point of contact between those two circles. And we also know that the small circles have three tangents. This tangent is tangent to the circle at point S. This tangent is tangent to the circle at point Z. And this tangent is tangent to the circle at point M. Actually, points S, Z, and M are also defined as launch points between the circle and their tangents, and its tangents. Okay, points Z, M, and S are defined as launch points between the circles and its tangents. Okay, and we also know that AC equals to 9 units, DB equals to 4 units. This is a right angle, so this is also a right angle. This is a right angle, and this is a right angle. In the next step, we drew 3 radiuses to the launch points. The 3 radiuses that we drew exist from the center of the circle, that is point Q, and touches the circle at the launch points. Here it touches the circle at point S, that is the launch point. Here it touches the circle at point Z, that is also the launch point. And here it touches, the radius touches the circle at point M, that is the launch point. The launch point between the circle and its tangents. Okay, so we actually have rule number 1 that states that the tangent to the circle is perpendicular to the radius at the launch point. Okay, so according to rule number 1, this tangent to the circle is perpendicular to the radius that is drawn to the launch point. This radius is drawn to the launch point, that is to say to point S, and therefore according to rule number 1, the tangent is perpendicular to that radius. And also here, this tangent is perpendicular to the radius that is drawn to the launch point. Actually, this radius touches the launch point, that is point Z, so that radius is drawn to the launch point. Therefore, according to rule number 1, the tangent is perpendicular to the radius. That is to say, this is a right angle. And also, here we have the radius that touches the launch point, that is to say, touches point M. Therefore, those angles are right angles, because of the fact that the radius is drawn to the launch point, point M. Therefore, according to rule number 1, the tangent is perpendicular to that radius. This radius also touches the launch point, point M. Therefore, the tangent to that circle is perpendicular to that radius. That is to say, this is a right angle and this is also a right angle. Okay, so actually we created here quadrilateral QZ MD that has 3 right angles, and the sum of those 3 right angles is 270 degrees. And we have rule number 2 that states that the sum of the angles in a quadrilateral, according to rule number 2, the sum of the angles in any quadrilateral is equal to 360 degrees. So we have already have here 3 right angles that the sum of them is 270 degrees. So the fourth angle must be equal also to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. Okay? The value of angle number 4 must be equal to 360 degrees minus 270 degrees in order to complete the sum of the angles in quadrilateral QZMD to 360 degrees. Therefore, the fourth angle must be equal also to 90 degrees in order to complete the sum of the angles in quadrilateral QZMD to 360 degrees. So the fourth angle is also equals to 90 degrees. So we have in this quadrilateral 3 right angles, and according to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. Okay? So this quadrilateral has 4 right angles, according to rule number 3, therefore it is a rectangle. So quadrilateral QZMD is a rectangle, and we have rule number 4 that the opposite sides of a rectangle are equal to each other. So actually, according to rule number 4, QZ that is opposite to MD is equal to MD. QZ equals to MD. Okay, QZ equals to MD, but we know that QZ is the radius of the circle. QZ also equals to R, so we can derive from this equality that MD equals to small r. MD equals to the radius of the small circle. And we also have the second quadrilateral, that is SQCM. Quadrilateral SQCM has 3 right angles, therefore the fourth angle must be equal also to 90 degrees according to rule number 2 that states that the sum of the angles in any quadrilateral equals to 360 degrees. Therefore the fourth angle is also equals to 90 degrees. So here we have a quadrilateral with 4 right angles. Therefore, according to rule number 3, this quadrilateral is a rectangle. Okay, so we have here a rectangle, and according to rule number 4, the opposite sides of the rectangle are equal to each other. So SQ equals to CM, and SQ equals to small r. So SQ that equals to CM also must be equal, so CM must be equal also to small r, because CM equals to SQ, and SQ equals to r, so CM also must be equal to small r. Okay, so we know that MD equals to small r, and CM also equals to small r, and we defined PM as x, that is to say PM equals to x. So the value of CM, the value of CP actually equals to CM minus PM. Okay, CP equals to CM minus PM. That is to say CP equals to small r minus x. Okay, then we created two equations for the radius of the big circle. The first equation states that the radius of the big circle is AP because P is the center of the circle, so AP is the radius of the big circle, and equation number 1 states that R equals to AP and R actually equals to AP plus AC. So R actually equals to 9 plus R minus X, and we created equation number 2 that states that R also equals to PB. R equals to PB because P is the center of the circle, so capital R equals to PB. And capital R equals to PB, that is to say capital R equals to PM plus MD plus DB, that is to say capital R equals to X plus R plus 4. So we created two expressions for the same radius. Therefore, of course, they are equal to each other because those expressions are expressions for the same big radius. So we can compare equation number 1 to equation number 2, and we got equation number 3. Okay, again, equation number 3 is a comparison of equation number 1 to equation number 2, that both of them are expressions of the same radius, so they are equal to each other. And from equation number 3 we got that x equals to 2.5 units, but we have equation number 1 that states that the radius of the big circle equals to 9 plus small r minus x, and we know that x equals to 2.5, so we can substitute x by 2.5, and we got that the radius of the big circle equals to 6.5 plus small r, and we also know that x equals to 2.5 units. So actually we presented rule number 5 and we implemented rule number 5 in our two circles. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So if two circles touch each other internally, then the distance between their centers equals to R1 minus R2 if R1 and R2 are the radiuses of those circles. Also D equals to R1 minus R2 when D is the distance between their circles. D equals to R1 minus R2. So we can implement rule number 5 in our two circles because here we have internal length between those circles at point N, that they touch each other internally at point N. Therefore, according to rule number 5, QP, that is the distance between their centers, is equal to capital R minus small r. Okay, according to rule number 5, QP equals to capital R minus small r. So from equation number 4 we got that capital R equals to QP plus R. But we have already known that capital R equals to 6.5 plus R. So we have two different expressions for the same radius. So we can compare equation number 1 to equation number 4 because both of those two expressions are expressions for the same radius. So of course they are equal to each other. So in this way we created equation number 5, and from equation number 5 we got that QP equals to 6.5 units, and we already know that X equals to 2.5 units. And then we connected together points Q and P by a straight line. and we created the green right triangle. This is the right triangle because angle QMP equals to 90 degrees. So in this right green triangle, we implemented the Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to PM square plus QM square, and we know that QP equals to 6.5 units, PM equals to 2.5 units, and the only missing variable is the radius of the small circle. So we solved this simple equality and we arrived to the final result that the radius of the small circle equals to 6 units. Again, the radius of this small circle equals to 6 units. Okay, thank you very much.